liquid, solid, plasma, gas.
Limitations of technology have taught us to believe that only 4 states of matter existed. But I'm here to tell you otherwise.
In the 1920s, physicist Bose challenged traditional quantum statistics of light quanta, arguing that you cannot have 2 photons of the same energy as being distinct and indistinguishable. Now, in later collaboration with renowned physicist Albert Einstein, they expanded upon this idea with atoms, hypothesizing a distribution of atoms with the same energy that don't interact and are indistinguishable. This was made possible because photons and certain particles shared an integer spin, later identifiable as bosons. One of the 2 types of fundamental particles, bosons, were named after particles that can occupy the same energy level. Let's take a deeper look into Bose-Einstein condensates. Take a handful of sodium atoms, for example, and heat it to 700 degrees Fahrenheit.
Each atom has its own energy and is able to move freely.
Once the atoms are separated, we begin the cooling process by shooting them with lasers. Hey Joy, sorry to tell you, but lasers are hot. Ironic, right? Now when you think of lasers, you might be thinking of the phasers from Star Trek where they vaporize things. But here, they're used for cooling.
They're used as recoil. Imagine a game of billiards where the cue ball strikes a ball at rest. The cue ball elastically collides with the ball at rest and maintains the conservation momentum by slowing down. Similarly, when we hit an atom with bursts of photons, eventually they will collide head-on. And when they do, Newton's third law of motion, right? Every action has an equal and opposite reaction. It acts like a shove in the other direction, thus slowing the particles to an even lower energy.
When the gases cool down, the atoms have negligible free energy and hardly move relative to each other. But because of their quantum nature, the atoms begin to behave as waves, and the particles begin to lose their individuality. Essentially, the particles themselves begin to lose the physical properties that once made them identifiable, such as velocity and position. At very low temperatures, all the bosons are able to occupy the very same energy and the same quantum state. They all form a single quantum collective wave called the Bose-Einstein condensate. It provides physicists with an extraordinary opportunity to analyze quantum effects at a larger scale. The intellectual pursuit of new forms of matter at ultra-cold temperatures revealed superconductivity and the frictionless creeping of superfluid helium. And if you thought lasers with lights are cool, future advancements predicts the possibility of an atomic laser, which can be utilized in atomic clocks, quantum computing, and even quantum teleportation. Bose-Einstein condensates is only one example demonstrating achieving the impossible through technological progress.